Howdy folks. So I recently bought one of these 16.2 volt capacitor banks off of eBay. These are pretty common. It's basically just six 2.7 volt caps in series. They come in a bunch of different capacities, but I found a good deal on this one, which has 500 farad caps. They're Sanwa branded. Whether they're even genuine Sanwa is unknown, and Sanwa's not a great cap manufacturer. But of course, this thing was pretty cheap. It was, $20 odd delivered, so pretty good. And of course, it comes with this sort of balancing board. There's nothing really advanced on this. It's basically just a bunch of programmable voltage references with transistors and bleeder resistors. And the idea is that once the capacitor reaches 2.7 volts, the reference turns a transistor on, which then shunts the excess current through these resistors, which bleeds off the energy as heat. And that way, if you actually do put 16.2 volts across, no single cap will exceed its voltage. Now, these references aren't super accurate, so the cap may go a little bit over if you go all the way up to 16.2. I don't go up to 16.2. I've never taken it that high, and I don't really plan on doing that. But anyway, I bought this just because I wanted to play around with super caps. I mean, I ordered some way back in June, and they never arrived. I lost my money. I wasn't even able to get it back. So I ended up ordering these, and they actually arrived. So finally, I get to do some experiments with super caps. I thought, okay, well, what can I do? And I remembered I had this. This is actually a UPS. So this is a Tripp-Lite Internet Office UPS. It's I think it's like a 300 watt or maybe even 300 VA. It's got a model on the board here, Internet 550V or 550U. So it's not a great UPS. I got this from work. Basically, the battery had died, and the IT at my work said, well, because there's no battery door, we can't replace the battery, so they just chucked it. And of course, you can take the battery out, and it was totally dead. And so I've just sort of had this for a while. I have no real use for it, and I didn't want to buy a battery for it because it's not a big, powerful UPS, and of course, it's not pure sine wave, so it doesn't really, I don't really need it, is really all I was getting at. So I thought, well, these things, of course, use 12 volt sealed lead acid batteries, and they need them because of the high current. And well, Supercap Bank can provide high current, and this thing is rated for 16 volts, which is above the max charge voltage of an SLA cell, which is around 13-ish, 14-ish volts. So I thought, well, what if I were to just use a capacitor bank in a UPS? What kind of performance would I get? And of course, this is dead simple to do. So as you can see, I've just got this thing open. It is actually live right now, so I'm not touching this. But I've just connected the battery terminals directly in the most janky way possible to this cap bank just for testing here. And this UPS will charge this no problem, because all the UPS charge circuit really is just a constant current limited power supply that charges up to a fixed flow voltage. Charging a lead acid cell is nowhere near as complicated as charging a lithium ion cell. So these things are pretty dumb when it comes to charging. And so they'll charge a cap bank happily without any problems. And so if I actually measure the voltage on this, it's about 14.2 volts. That seems to be where this thing charges up to. And because I'm going to actually sort of package this up nicely, because this actually works pretty well, I'm going to take this board out, and I'm going to see if I can change what that flow voltage is. Because if this is indeed just a regular power supply, there may be like a resistor divider or something I can alter the values of to float this thing up to 16 volts, which would get me a lot more capacity out of these caps. It's still acceptable at where it is now, but if it's not a dedicated lead acid charge chip, which I doubt it is, I can probably make this thing charge to a higher voltage. And that's pretty much all that you really need to do. And my goal for this would be to have something that is incredibly low maintenance and can still provide a short duration of backup power. So the advantage to using a supercap bank instead of a lead acid cell is that this won't fail in 5 years. And it's sort of this thing will sort of last, I don't want to say last forever, but it will last a much, much longer time. In fact, most likely the UPS will fail before the caps do. That's the idea. with a UPS like this, I'm not really looking for massive runtime or for really high output loads. I mean, I have really big UPSs for my big stuff, and most of my power failures, they're not tens of minutes, right? They're usually just a couple seconds, like 5 seconds, 30 seconds, not really long. So as long as it can hold that up, hold up, a moderate load for that amount of time, it's perfectly adequate and very viable. And so I've actually done a load test on this, and I'll demonstrate that. So the lights that I am currently under right now, it's just a CCFL and an LED light. They're plugged in here, and they're drawing roughly 25 watts. And I'll prove that to you. So yeah, that goes out to 0. So those are my lights. And 25 watts, and their power factor is not too great, so it's about 41 VA. So, this is a pretty typical load that you might expect. If you have some sort of simple equipment, maybe you've got lamps or alarm clocks or other small things, you want to ensure they don't lose power. And also, you could also run higher loads, but for proportionally less time. So I'm going to plug this into the UPS, and we'll see what happens. So I've got the lamp. I've moved it from the kilowatt onto the UPS, and our batteries are full, or our super caps are fully charged to 14.2 volts. And I've just got the UPS plugged into this power bar. So I'm just going to switch the power bar off, and we're going to watch it switch in. So you can see that the voltage does go down quite quickly. And the alarm will probably start sounding. There you go. And as you can see, the lights are still on just fine. And I've tested this, and this 25 watt load will go for about 1.5 minutes on a full charge, basically. So I will shut this off because that alarm is annoying. This UPS takes a while to kick in after the power comes back. There we go. And it immediately starts charging back up. So yeah, this thing cuts out about 10.2 volts. So that gives me about 1.5 minutes of runtime on that kind of a load, which I think is perfectly adequate. I could get quite a bit more runtime if I increase that voltage, which like I said, I'm going to try and do that. But even this is perfectly adequate. I may actually get a bigger load just to demonstrate how quickly it discharges on a higher load. But yeah, I'm actually pretty happy with how simple this is. I think what I'm probably going to do is just drill some holes in the side of this case to put these wires out, properly solder these spade terminals directly onto the big ring terminals of the board. I'm not going to bother to. I'm never going to use these F terminal connectors again, so I don't really care. I'll just solder directly to them, and then I'll just enclose this cap bank in something protective. I'll probably cover the top in Kapton tape and maybe build a little box around it or something. Maybe make it clear. I'm not really quite sure, and I'll just basically attach it to the side of the UPS because quite nicely this is almost the length of the UPS, so it'll actually fit into a pretty nice package. So one thing that I'll note is the power consumption of a setup like this. Of course, UPSs, they're not free to operate, right? They're always on, they always consume some amount of power. And so if you have a bunch of them, they are going to make some amount of difference to your power bill. But the Supercap isn't really going to change that. These things have very low self-discharge. These things, after a few days, they only lose a couple volts. And so this unit, fully charged, appears to be about 3 watts. Which for me, that's pretty much negligible power consumption. Most of my other UPSs are about 10 watts, so this is actually a very good setup actually for what it's doing. So I wanted to do a load test with something a bit more than 25 watts, something around 150 watts. I wasn't really able to find very much that I was willing to try on this, but I did actually find a corded drill. And of course, you're not supposed to run inductive motors off of UPSs, but I don't really care, and it seems to be okay with the power factor when you run it at full tilt. So with this motor just sort of freewheeling basically, it's about 150 watts at 200 VA, which is within the spec of this UPS. And so basically I've got it fully charged, and I'd like to just try and run it till it's dead and see what kind of a runtime I get. Now I don't have enough hands to do this, so I'll inset that the amount of time it actually runs for in the video. I'll have to come up with that after editing. I don't have enough hands to operate my stopwatch, and I can't find my tripod right now. Okay, so we have the power consumption of the unit, which will be about 150 once I start the drill. This is the battery voltage, or the capacitor voltage, and the switch to turn the UPS mains power off is here. So I'll turn the drill on. You probably won't be able to hear me after that. We got about 150 watts here, and I'm going to switch off the power. There's a low battery alarm, and it switches off at about 10.2 volts. So, I mean, that was still a decent enough runtime that, you know, I would say that power glitches and stuff are definitely going to be within that amount of time. So even if you were running a full, you know, home PC setup off of this, or, you know, like a small desktop setup off of this, it could still be useful. So anyway, let me take this board out and see what's on the backside and see if I can change the float voltage. So it's been about a week since I last filmed any footage for this project, and quite a lot has happened in that week. So I apologize if I am repeating myself, but I've done quite a bit of work on this, and the project is pretty much functionally complete. There's just a little bit of hardware, sort of mechanical stuff I'm going to do, and I'll show you the finished product at the end of this video. But originally I set out, of course, to basically boost the voltage that the charger outputs so that I could you know, charge these capacitors up to 16 volts instead of the 14.2 to get more energy storage out of them. And so I went through to reverse engineer this to change that. And I want to show the process that I went through to actually identify what I needed to do on this board. So I'm going to go through that process. And also, there were some problems that I encountered after I had changed the charge voltage regarding the under voltage and over voltage protection on this device. And so there was more reverse engineering I had to do. And then I had to come up with a solution that would allow me to effectively, without changing the software on this, which is something I'm not able to do, get it to accept you know, voltages it was not designed to accept. And I had to make a couple design decisions, and so I want to go over the pros and cons of the design choices I've made, and you know what are the sort of the downsides of doing what I've done, how it works, and some of the things I tried which didn't work. You can see now there's this this little mod board here with some active circuitry on it, and I'll explain what that is and what that's doing in just a moment. But yeah, I just want to go over sort of after I've done it all, what I did in what order. Of course, the exact details are only going to be relevant to people with this exact UPS who want to do the exact same thing I'm doing. But of course, this principle of going through things and how I did the reverse engineering, that is something that is applicable to anything electronic. So this is the back of the board, and ignore the wiring and everything. I'm going to go over that when I get there. So basically, the first thing I needed to do, of course, was get the charge voltage up. So I needed to find the charge circuit. And of course, that's going to be controlled by an integrated circuit. So of course, there's a bunch of ICs on the back of this board, and we need to find which one of those is responsible for charging. And so basically, you can start Googling part numbers. Of course, this is an STM microcontroller, so this is going to be, of course, the sort of the main processor with all the software and everything, and probably the computer interface. By proximity, this is likely an E² PROM, given the fact that it's an 8-pin device, and of course you can Google that. Yes, it is an E² PROM. This part in the center here just says 324 on it, nothing else, so likely it's an LM324 quad op amp. You can just sort of assume that there's going to be an analog part in here. This part down here, this is another ST part, and this is a PWM power supply chip, so this could be of interest to us. And this last chip up here is a Texas Instruments PWM power supply chip as well. So this is also of interest to us. Now, of course, a device like this is going to have effectively two power supplies. One on the output, which generates one that runs the inverter, and then one that charges the battery. And so which one is which in this case? Well, you can simply just look at the other side of the board and figure this out. So of course on this side of the board we have two transformers. We have this big transformer here with these main switching transistors, and then we have this much smaller transformer over here. And so it's pretty easy to see that this stuff on this side of the board is all the output. So we have our main switching FETs, then our output transformer, and then the stuff that makes the modified sine wave. And then over here we have a little small transformer which likely runs all the digital circuitry on this board as well as the charging. And so by just looking at where the proximity of these two chips to that circuitry on the other side, this guy is most certainly the main output chip, and this guy is most certainly the charge controller. And so this is the supply we're most interested in. Of course, the first thing you want to do is you want to get the data sheet for this. And being from TI, it is very easy to find this data sheet. You just put the part number in. It's one of the first results. And what we really want out of that data sheet is a reference diagram, a reference schematic. Because, of course, I'm not speaking for all electrical engineers, but generally when you are designing a circuit, you have requirements for your circuit, and you're looking for a chip, that can meet your requirements. And you need to design a circuit around that chip. Of course, it's not just put the chip down and it magically works. There's a whole bunch of other circuitry that you need to implement with passive components and other things to make the chip work in and meet all of the requirements you have. And so generally you're going to look in the data sheet for that part, and you'll find the manufacturer will provide some circuit, maybe more than one, about how to use it. So they'll provide a reference schematic, and they will tell you all of the specifications that circuit meets. They'll give you diagrams and measurements and error factors and all sorts of things that they have basically tested the part in that configuration. And a lot of designs start with that circuit, that reference circuit, and then they are simply modified and tweaked to fit in the to the specs of the end design, as well as maybe some cost optimization, things like that. And so what I was hoping for was that this UPS would implement a circuit very similar to the reference schematic in the data sheet. And so I found the reference schematic in the data sheet, and basically what I wanted to do was find out, are they using that or something close? And of course, the schematic looks nothing like this board. And so, where do you even start? And so what I wanted to do was I wanted to try and find big, obvious components that would be very easy to identify and start tracing the circuit board from that point. Now, what's nice about this board is that it's all single-sided. There's no traces on the other side of the board. Everything is on one side, and they're just using jumper links. And as a result, there's no internal layers, none of that stuff. And as a result, there's no, you could with a magnifying glass trace all of these traces around, and you wouldn't miss anything, which does help. Of course, ultimately, you want to use your multimeter in continuity mode to check what connects where, but this is one of the most simple things you could possibly try and reverse engineer, just by the board design itself. So originally, I noticed that there is an optocoupler in the circuit, and this is used for feedback from the secondary side. And so I wanted to see, can I find an optocoupler? Of course, they're going to be a big surface mount or a big through-hole component. It's going to be, of course, on this side of the board. And if you look right down here on the board by the transformer, there is a single optocoupler near this sort of what we're calling the charge circuit. And so, of course, it's only got 4 pins, and so you can easily line up those 4 pins with the schematic. And so now that I knew where the optocoupler was, it's these 4 pads here, I could then branch out and start tracing, resistors and capacitors and other things from either side of the optocoupler. And the data sheet, they talk about, in the reference design, they talk about how you set the output voltage. And in their reference design, there are 2 resistors, Ri and Rk, and they basically say, one of these resistors is fixed, and the other value, to come up with the other resistor value, you plug in what you want into this formula, and it gives you the value you need to get the output voltage you want. And so ultimately what we want to do is find Ri and Rk, or their equivalent resistances in this design, if they exist, and then we can change them. So I wanted to find if they existed, and the other big component, aside from the optocoupler, that would be pretty easy to find is this TL431 programmable voltage reference. And of course, those usually come in TO92 packages. And so flipping the board over, we look for a TO92 package part, and there's this U12 here on the board. And if you read that, it is a TL431. So clearly, they're using that as a reference on the secondary side. And since that's connected to Ri and Rk, I trace them out on the board. And so Ri and Rk are actually found over here on this board. And so one of the resistances is actually made up of 2 resistors in series. So note that when you're reading a schematic, they represent, a resistance is a single resistor with a certain value, but sometimes you can't get that value, and so you simply put multiple resistors in series. Or sometimes to get the voltage rating or the current capability, you'll see multiple resistors in series or parallel. And in this case, there's 2 in series. And so once I'd found one, I then sort of used the formula, computed what the other resistor value was, and so I knew what I was looking for. And then when I found the resistor that I thought was Ri, I believe, I measured its value, and its value was exactly what I expected it to be according to the math, and so I knew for sure that was the resistor value. And so that gave me enough confidence that at least the way they were doing voltage feedback was the same as the reference schematic. And so as a result, all I needed to do was, I wanted 16 volts or roughly 16 volts out, so I put that through the formula. It gave me a resistor value, and I simply replaced one of those resistors with a new one. These are just 0603 surface mount resistors. I just replaced it with a different one, and that's all I needed to do to set the output voltage for the charge circuit. So that was a relatively straightforward change. And of course, that was originally all I set out to do, and that's all I thought I would have to do. But I, of course, forgot that this device, of course, has some safety built into it. And so what I noticed was it would charge up to about 14.2 volts, and it would keep charging. It was clearly outputting, like if I basically disconnected the caps and just left the outputs floating, there's a big capacitor across the output. So the power supply will charge the capacitor. So with nothing connected, you can actually measure what the sort of the max charge voltage is instantaneously once the thing powers up. And it was sitting around 15.7 volts, which is fine with me. I left it at that. That's it's within tolerance for me. And it would sit there for a minute or two, and then it would shut off. And it would kill the charger. The entire unit would shut down. And that's when I sort of realized, oh shit, there's over voltage protection in this. This microcontroller or something here must be sensing that the battery has gone above its maximum, and for safety, just kill it. Just stop working. And so I had to find how they're doing over voltage. And there were two. Now this was a bit harder to solve than the charge circuit, because with the charge circuit I knew sort of where to start, but with the over voltage I didn't know if there would be a hardware implementation or a software implementation, because you can do this in one of two ways, right? There could be some sort of hardware circuit, a voltage reference, something that, a comparator or something that actually checks the voltage against something and then, physically cuts power, or they're doing it in software. There is some sort of analog input into this micro here, and the software is voluntarily shutting down the system if the input voltage goes too high. And so I wasn't really sure where to start. Of course, there's a lot of pins on this microcontroller, so knowing what they all do, it takes a lot of reverse engineering, and it was a lot of effort that I really didn't want to go into if I didn't have to. So I started sort of working around where I was before, trying to see if I could find anything hardware-based, because that's what I originally thought. It would be a hardware-based solution. And I wanted to find a voltage reference. And of course, the easiest voltage reference you can get is a Zener diode. And so I was looking around to find a Zener diode in here, and I did ultimately find one. This little part here, D12, is actually a 14.2 volt Zener diode, which just happened to correspond to the maximum voltage that it would allow you to charge the battery to. And so I thought for a short period of time that this was actually what they were using for the hardware protection circuit, because there's some transistors over here that are connected to that Zener, but removing it actually did not affect anything, and so it's actually just there to protect the transistors. It's actually completely irrelevant when it comes to the overvoltage protection. So that was a red herring, and I wasted a little bit of time on that. So after sort of looking around, not seeing anything else that was sort of relevant, no other voltage references, things like that, especially anything around this LM324 here, I thought at that point it's probably a software-based approach. And so basically what I did was I wanted to basically check the pins of the micro and see if I could find any analog voltages. So of course it's a 5-volt microcontroller, so we're going to expect to see ground at 0 volts, 5-volt TTL logic signals, but of course this is going to be an analog signal, which means it's going to be somewhere in between. It's going to be a weird voltage, and so I wanted to find the pins on this thing that have weird voltages on them. And I found a couple with 3.3 volts on, but that's a standard logic level. That's most likely the E-squared problem. So what I did was I actually took some of my power resistors. So I remember I showed these in a previous video. And so basically these are just 8 ohm 100 watt power resistors, and I just connected this across the output of the charger. I actually put both of these in series for 16 ohms, and that loaded down the charger enough that the charger wasn't fully charged. It was like, I don't know, like 11 point something volts, so right in the middle of its charge range. And so that would provide a weird voltage. And so I probed around and I found 2 pins that are common together actually on this end of the micro here, and they had a weird voltage. And when I disconnected one of the leads from the resistor, and of course the voltage on these wires went up, I saw the voltage on those pins go up as well. And so the voltage on those pins was tracking the voltage here. And of course it wasn't the same voltage. Of course this was less than 5 volts, and this of course was over 10 volts. There was obviously some sort of divider involved. But those were clearly an analog input into this micro, and so that was the best thing that I could find. And so I wanted to sort of confirm that was indeed what was doing the overvoltage protection. And so what I did was I found basically a resistor that connected basically this pin to the basically through some transistors and some resistors up to the positive rail of the battery, and this R116 here, I pulled that out, and then I actually connected a diode, just a standard like 1N4001 diode, between the VCC, which is the 5-volt supply rail, and those pins. And so that would give me 4.3 volts on that pin, right? Because 5 volts minus a diode drop would give me 4.3 volts, which is something that it would accept. And so basically, once I did that, I had sort of fixed that voltage. I noticed that I could charge the thing up as high as I wanted, and it wouldn't shut off. And when I discharged it, it also wouldn't shut off on the under voltage. So they were doing both the over voltage and the under voltage on that pin. Also, things like the under voltage alarm, like the low battery alarm, would not fire anymore. And so that was good. And so originally I thought, oh, I can just disable that pin, tell the micro the battery's always half charged or whatever, and it's fine. But unfortunately, they have actually used that for another function, and that is the output voltage regulation. So, of course, as the battery voltage goes down, the inverter needs to work harder to keep the output voltage at 120 volts. Otherwise, the output voltage would go down. And so the microcontroller is actually responsible for controlling this power supply chip to get the desired output voltage. And so by defeating that input, when the supercap was fully charged and I started up the inverter, the voltage was actually higher than the 120 volts, and then it would drop, and because it would actually never brown out, it would actually go down to like 60 volts, and the inverter would still be running. And of course, you definitely don't want that. You want this thing to cut out once it can no longer regulate proper mains voltage anymore. Otherwise, whatever you've got plugged in, weird stuff could happen. And similarly, this control chip down here, this STM chip that drives the inverter, its data sheet says that it's only good down to 8 volts. And so I wanted this thing to cut off at 8 volts when this thing would become unstable. And so I was kind of faced with a conundrum here because they were using a voltage divider effectively to get an input into this. And so this thing its low voltage cutout was 3.4 volts and its high voltage cutout was 4.8 volts. And so you couldn't have it ever go outside that range. But what I wanted to do was I wanted my supercaps to be able to go between 16 volts or 15.7, which was the maximum voltage, down to 8 volts, because that's what this thing would run off of. That would give me the most energy out of these caps that I could get with the circuitry on this board. But the problem is that's a nonlinear scaling of this analog input range, because if it was simply shifting, simply shifting up or down the range, you could easily do that by just changing one or both of the resistors in the voltage divider. But because I wanted to expand the range of voltages, that wasn't going to work, and so I needed some other solution. So I've just grabbed a bunch of schematic drawings and stuff. Don't try and make sense of these. They're not very accurate. But this is all some of the stuff that I was sort of reverse engineering while I was doing this project. And anyway, the solution that I came up with was to use, the first solution I came up with was to use a Zener diode, basically as a shunt regulator on the input pin to the micro. So the idea would be I would change one of the resistors in the divider. The divider was R160 and 117, which was originally a 10K and a 5K. And so I would just basically drop R116 down to 6.8K, and this would shift down the minimum, the under voltage would then cut out at 8 volts instead of the 10.2 or whatever. And then the Zener would prevent the micro pin from going above 4.7 volts-ish. And the idea would be that you would have some amount of error at the high end of the capacitor voltage, and then once this thing stops conducting, you would have a constant fixed error for the remainder of the discharge, i.e. the mains voltage being produced by the inverter would be off from the correct voltage by a fixed voltage for the duration of the discharge. And I thought that this would be fine. And so I ordered some stuff from DigiKey, and so I ordered some 4.7 volt Zeners while I was at it. And so I built this up. It was pretty easy to put on the back of the board. And ultimately, it didn't work because the Zener, in order to get the proper Zener voltage, you need to have a specific amount of cathode current through the Zener. And the circuitry that's above here wasn't allowing enough current. I should have checked this when I calculated these values. I should have checked what the current was. But anyway, the Zener that I bought did not have enough current, and so it regulated to about 3.9 volts instead of 4.7, which royally screwed things up, and it really didn't. The error was really really bad. It was outputting like 150 volts, which was not okay as far as I was concerned. So I sort of took this out, and this wasn't going to be a workable solution. So I wanted to do something similar to this, but I wanted something that would work on lower cathode current. And so, of course, whenever you're thinking about references, ultimately the venerable TL431 comes to mind. And so the TL431 is a ubiquitous programmable reference. So it's like a programmable Zener diode, and you can give it closed loop feedback. And as long as you give it like a milliamp or so of cathode current, it will happily regulate off of that. And so my idea was I would basically do the same thing as this, but instead of using a Zener, I would use a TL431 and then 2 resistors, which would then set this to be equal to the 4.7 volts that I wanted. And so originally I sort of came up with this kind of design. I would leave in the original 5K, and so then I'd have this 5K in parallel with this. And ultimately the values changed a bunch because as I did math, because there's a bunch of things I had to satisfy in this circuit. Basically, you have to satisfy the minimum current through the TL431. You also have to ensure that these resistances in parallel with this resistance gives you, with this resistance, the correct undervoltage cutoff. You also have to make sure that this resistance can provide enough current for this after these have already taken their share. So there's like a little balancing act you have to do to get the values right. And I really screwed up because I don't know, I originally built this for some reason, which I don't know where I came up with this number. But anyway, I should probably have drawn this nicely for the video, but I honestly couldn't be bothered anymore. So basically there's a 4.3K for R116 now. I've left this in, it's X'd out, but that is left in. And basically I have a 5K resistor here as 5K and then a 4.7K here. And this gives me a 4.8 volt clamp on this node, which works very, very well. And so basically the way I've implemented that is I've just got 3 wires here, 3 mod wires. One is ground, and that's for the anode of the Zener, and then I have 2 which go across R116, which is a resistor I've had to make up, the 4.3 I had to make up from a 3.3 and a 1K. And so I've got this little mod board here, and this is it's got the TL431 there, and it's got the 2 resistors that make up R116. It's got the other resistor that makes up the R1 value for the biasing, and then there's a trimmer pot which ultimately just got set to its maximum because I screwed up one of the values, but it works anyway. And so this thing, I'm just basically going to wrap this in some tape and sort of glue it to the side of the case so it can't touch anything, and that works well enough. And fun fact, this TL431 actually came out of that compact QVision 210 monitor that I scrapped like a year or so ago. I keep the boards to stuff that has a lot of good components on it, and I didn't want to spend another $8 on shipping going to DigiKey, so I looked through it and I found it had the part on there, so I just desoldered it, and it's a 20-something-year-old Zener TL431, but it's the same part and it works fine. So that's where that came from. So anyway, so I tested this, and at maximum capacitor voltage, the error is very little at all. It actually outputs 125 volts, so it's really not high at all, perfectly within spec. And as the cap voltage goes down, it seems to regulate. Of course, it does go down linearly. There's no like jumps or anything, because as the voltage goes down, the Zener draws less and less current, and so ultimately the voltage does go down slowly until it gets to about 100 volts. And so the error is effectively 15 volts, because this thing is spec'd at 115 volts output for some reason. So it's a 15-volt error. And 100 volts is what it will regulate all the way down until the thing cuts out at like 8.2 volts or whatever, just due to the tolerances of the resistors, and everything's like 5% tolerance. So, I knew things weren't going to be exact, but it's close. And 100 volts sounds low, and it is low, but it's actually fine because basically everything that is a universal power supply is rated for 100 to 240 volts. Actually, I think I have one over here. Yeah, so like most universal supplies are rated for 100 to 240 volts because 100 volts is, I believe, what they use in Japan. And so there's obviously a tolerance on the 100 volts, so you can actually go a little bit lower than 100 volts, and everything should be okay. So if you're using anything with like a switching supply, as long as it's universal, it'll be totally fine with a slightly lower voltage. And so, with the things that I'm going to be plugging into this, I'm totally fine with that, and that's just something you're going to get with this kind of modification. Of course, if I could edit the firmware in that micro, this would have been perfectly solved. Would have gotten the exact voltage range I want, perfect regulation on the output. It would have been super easy, but of course, it's code-protected microcontroller. I can't dump the code in it, and I don't want to put my own microcontroller in there because, of course, there's a lot of safety built into something like this, and I could very well overlook something, especially because I didn't design this circuit. And I really don't want this thing burning my house down, so I'd much rather just simply do this modification and live with the error than try and rebuild the software to do something differently. Of course, one other thing I could do, which is kind of ridiculous, but I could do, is I actually could put a microcontroller. This was something I did actually consider at one point, was put in a microcontroller that basically reads the output voltage, and it does some computation and generates an analog voltage via like PWM with like an RC low pass filter on the output, and puts that into the analog input of that micro. And so it basically forces the original micro to do the output regulation like basically it's like a dual microcontroller feedback loop, which I could have done, but that would have been a lot more work, and this was just sort of like a pilot project. So maybe if I get a bigger UPS, a better UPS with much bigger and better supercaps, then maybe I'll do that. But maybe the circuit won't be as weird, so who knows. So anyway, I think that is all I really need to go over. You'll notice that there's this big hole in the side here that I've dremeled out, and so basically I'm going to take the capacitors and I'm going to hot glue the board in, and they're actually just going to stick out the side of the case. And I think that'll actually look pretty cool, rather than having a little bolt-on box. I tried to find one, but I couldn't find one that fit. Sorry, my camera battery died. So anyway, so I finished up the project, and this is what it looks like now. So I've got it all back together. As you can see, it's running, and the capacitors, they just stick out the side here. I've just hot glued them, that whole board in to the cutout that I have. The cutout's just a little bit smaller than the caps, so you can slide them in, and then I've soldered the terminals, and everything's back together, and it's working great. So yeah, I think it actually looks, quite cool actually with all these caps on the side. I chose to put the labels on the top mostly because of where the terminals were. It would have been impossible for me to solder them if they were at the bottom. And I actually can put probes in and measure the cap voltages. It's pretty recessed, so I'm totally I'm okay with, there's nothing that's really going to get up in there. I could put some tape or some kind of flange around here if I really wanted to, but I think it's safe the way it is. But I think it looks very cool with the caps sticking out, and they're other than that, it's looks like a bog standard UPS. And of course, as for performance, so originally I did test, and of course my 40 VA sort of lighting load that went for 1.5 minutes. Back when it was using the standard parameters for the min and max voltage. And so now the unit will run the exact same 40 VA load for 2 minutes and 45 seconds. So it almost doubled the runtime of this device. So I'm very happy with the performance of this. And for what it's going to be doing, I think this is more than adequate for the short blips and stuff like that. Having a low, basically zero maintenance device, I think that's that's pretty neat. And I'm surprised that I mean I'm sure that there are companies that make supercapacitor based UPSs, but they're definitely not a consumer product yet, at least as far as I know. But it would be cool to see something like this become a consumer product sold here in North America, so you don't have to build your own. But yeah, I mean, if you're comfortable working with mains electronics and stuff, and supercapacitors, things with massive output currents and stuff, if you're comfortable doing that, this is an interesting project. And if you, I wouldn't say buy a UPS just to do this, but if you have one that's got no battery in it, it's a cool project. And I spent no extra money. Really, I mean, the battery for this cost as much as the capacitor, so really it was just the cost of some resistors and some miscellaneous parts. So mostly it was the time to do the reverse engineering, and that unfortunately is something that you're probably not going to get around, because I don't think that there are schematics for any of these UPSs just floating around online, at least none for this model anyway. So anyway, I will stop waffling now, and as always, thanks for watching.